Hi, everybody. Thanks for joining me. My name's Tom Carruthers, and today I'm going to be talking you through one aspect of MERA, that's Method Evaluation and Risk Assessment. And what I'm going to talk you through in this tutorial is the quantitative questionnaire part of MERA that allows you to specify the fishery, population management, and data collection dynamics for a fishery. And in that way, characterize an operating model with which you can test harvest strategies, aka management procedures, in management planning mode. You can quantify stock status in status evaluation mode, but you can also check your management performance as you use an MP by looking at those simulated data coming out of the operating model relative to the ones that you're actually observing in reality. But today is all about this quantitative questionnaire. What I'm going to do is load up an example MERA file. Here we are at the MERA front end, and you can see we've got here at apps.bluematterscience.com/MERA. You'll also find a link from this in this presentation. I'll try and do it now. And you'll find that you can go to merafish.com as well to get these links. That also has some of these example MERA case studies. The one we're going to load right now is for tiger flathead from the Southeast Australia. Under section 1, characterize the fishery system, you will find the quantitative questionnaire, and it has 3 parts to it. One is labeled fishery. You can see this tab here, and there are 19 questions in the fishery tab. There's a management tab for which there are 7 questions, and a data tab for which there are 4 questions. We're going to start with the fishery one. Now, the very first panel of the fishery tab is the fishery description. And this gives you a place to name the common name, add the species name, the location of the fishery, the agency that manages it, and provide information that when the fishery had a meaningful start, there was meaningful impact of exploitation on the stock, to the current year of data that you may have for that stock. The reason we're using tiger flathead is it's a well-known example, and this is working off, I think, an assessment that was undertaken in 2013. So these text boxes give you a place to document what your species is and also who you are, but below it you'll find a much bigger text box which allows you to provide greater detail and even links to documents that you've used to specify your questionnaire. Here we're using something that's been assessed with a stock assessment. And that has the advantage that you can follow along and see how the justifications were made. But you should know that MERA was really designed for contexts where the stock in question is data poor or data moderate. So we want to characterize our fishery. We've described roughly why we're doing this and where the supporting documentation is. It's on to the next fishery question. One of the most important aspects of fishery dynamics that controls productivity and stock size is the natural mortality rate. And here, according to stock assessments, the M range for tiger flathead sits between about 0.4 and 0.2. And you can see in this figure, you've got a graph showing you roughly what you selected. That's equivalent to a maximum age in the range of about 10 to 20 years. Whenever you do a question in MERA, you'll find links on this side and a description of what this all means. But needless to say, when you select more of these or even make it unknown, you get a much wider range of specified year ranges and M values. Let's go back to the default, which was for a moderate lifespan. Whenever you first come to MERA, I've loaded an example here. All the questions start out as unknown. So basically, you can proceed with this whole approach, even if you don't really know very much at all. It will just simply create a very wide range of simulations for testing possible harvest strategies, for example. And in doing so, it will be a more strenuous and rigorous test of those harvest strategies. So one advantage here is that you can, if you have justification, narrow the range of uncertainty to match your best understanding. The important aspect of this question and all the others is that you don't overstate certainty, because the philosophy behind operating models and management strategy evaluation, MSE, is to test robustness against an uncertain set of dynamics. But in this case, we have a fairly good idea. It's a relatively data-rich stock, and we're choosing this moderate lifespan. And in here, we provided justification for that, a page of the document that we cited in that very first page. The next question asks something that may not be readily understood, and that is how depleted the stock is. This is asking you relative to spawning biomass at unfished levels where you are today. And so 2 examples are provided here, where if you were to select depleted and moderately depleted, this is where they could end up. To give you an example, of course, you could choose other fractions. So in this case, a lot of the detail is in the low end, because if you were to specify a healthy stock, or let's say an underexploited stock, this is very robust to different harvest strategies, particularly the catch limits, where they're relative to historical catch levels. It really becomes necessary to have more detail when you get into the lower ranges of depletion, where it becomes ever more critical how you control for overexploitation or not. So this question is really structured around the idea that you need to know where you are in here. If you don't know, you do it with everything. If you do have an idea, try and remove implausible scenarios. You may not know this in a data moderate fishery, and you probably certainly don't know it in a data poor one, almost by definition. So let's start out again with what the assessment came up with, which is somewhere in the range of 15 to 30% of unfished spawning stock biomass. That's where it thinks we are today. And again, these are just example figures. This isn't the real trajectory of stock depletion. This is just showing you what this would mean for these 2 examples. Resilience. This is telling you to what extent you can expect the stock to still provide meaningful recruitment as the spawning stock declines. So this is often characterized by a parameter called steepness, which is the fraction of unfished recruitment that you expect to see at 1/5 of unfished stock size. So you can see the vertical line here at 0.2, that's 1/5 of unfished, and this is the fraction you're specifying. How resilient is it? When it gets down to 1/5, how much of that unfished recruitment do you get at 0.2 of unfished biomass? In this case, it's saying it's somewhere between 50% and 70% and 90%, which is a really wide range here. But of course, you could choose other scenarios. Resilience is one of the hardest things to quantify because it typically requires independent information about recruitment and spawning biomass. In data moderate fisheries, you could try to get at this by having an index of, say, age 1 fish against an index of, let's say, larger fish or something similar. But for the most part, you're going to have a high degree of uncertainty about this, and therefore a high degree of uncertainty about how quickly the stock will respond to low stock sizes in the future. And in this case, it may be completely defensible to say, I don't know. Again, we're going to stick with what the stock assessment says. But in a data moderate scenario, I would expect this to be very wide ranging. The historical effort pattern is asking you, roughly speaking, what you expect the pattern of exploitation to have looked at historically. This isn't asking you what the fishing mortality rate is. It's simply saying if you were to sketch how many fish boats were hitting the water or how many days of fishing were occurring, what did that roughly look like? And what this does is it constrains, roughly speaking, current exploitation rates relative to historical ones. You've got 2 different ways of doing this. You can draw it like this, so I can add data points in here if I want to, where we create a different trend, or you can enter coordinates into this box to sketch this. For the purpose of this, I'm going to do a quick demonstration. I'm going to try and remember what this looks like and try and recreate it. Here, by dragging down the data points to meet that high point and then bringing them down. You can enter exact data in here, or as I'll show you later, you can bring this in as a data file. But nonetheless, you can create your desired pattern and exploitation. Of course, if you've got uncertainty about this, there's 2 different ways of dealing with it. You could impose in the next question uncertainty around this, like kind of interannual variability, or you can create multiple MERA questionnaires and test the same management procedures you've had, or harvest strategies you're looking at, for different trends in the historical fishing effort. So let's stick with this terrible sketch that I've done. What we're saying is that was kind of like an average trend, but we expect there to be a little bit of movement around there. We could choose not variable, which follows it very tightly, an intermediate level, which has got interannual variability somewhere between 20 and 50%, or we could have a highly variable one. Just sketching the effort which we actually have for tiger flathead, we know this is going to be reasonably tight, but not very much so. So the intermediate level is chosen here. The way in which historical effort affects the impacts of stock depends on whether or not it's got more efficient. So per unit of effort, let's say per day, what's the exploitation rate been? And in many fisheries, you might expect that to be going up as they target that creature more intensively, or they become more intelligent. In other ways, the fishery may be trying to avoid those and it becoming less efficient. So this is the place where you get to choose that. The most stable version is between -1 and 1% per annum increased or decrease in your fishing efficiency. And that's roughly equivalent to halving or doubling efficiency over 70 years. So this is the bit where you turn that effort history into something that could be a relative fishing mortality rate. Now for tiger flathead, there's no expectation that the effort that's being used, which is roughly standardized anyway, to include confounding factors, that it should have major efficiency changes. But there are many fisheries in the world where they've targeted them strongly or similar, and you might want to consider different amounts of uncertainty in this historical reconstruction of fishing efficiency. Right, we're already up to question 7 of a total of 30 questions, so we're doing pretty well. Of course, in the future, you might have changes in fishing efficiency also. For the most part, you might assume they're the same as historical, but you don't know. And of course, this is going to fundamentally control the relative efficiency of an effort control fishery versus a catch control fishery. Some fisheries can really benefit from an input control, which is something like a size limit, a spatial closure, or an effort control. But in terms of effort, the effectiveness of that will, of course, depend upon how much we expect the efficiency to fluctuate in the future. For the purposes of this, we're saying it's stable, but you may really not know this. And it may be important uncertainty to include when you're trying to test a harvest strategy, particularly when you're choosing between catch and effort-based harvest strategies, because this one will affect the effectiveness of an effort control. So another thing that really that's important to specify is the relationship between maturity and what's called fishery selectivity. This is telling you essentially to what extent has the creature had an opportunity to reproduce relative to an opportunity to fish it as it grows larger. These are all here phrased in terms of the maximum, or let's not say maximum, let's say asymptotic length. So this isn't in terms of the biggest length you've ever seen. It's in terms of a length where the growth curve asymptotes. So the average maximum size of a creature or a fish in this population. And so we are phrasing here length at maturity, at 50% maturity. So that's where this horizontal blue line is here, relative to this maximum or asymptotic length. And in this case, we're saying it happens between 50% and 60% of the asymptotic length. Of course, what interacts with that is the fishery selectivity, which is the next question. And in this case, we're actually saying they can select for fish that are shorter in length than the 50% maturity. So they're either the same, it's got roughly the same upper bound, but could go a fraction lower. So roughly the same as the maturity curve, but not exactly. Big discrepancies in these things will strongly affect the sustainable rate that you can fish a stock at. For example, if you only catch really mature fish, it may be possible to catch really high fractions of them since they've been given an opportunity to reproduce. So this can be a very strong determinant of how hard fishery can, how high an exploitation rate can be on the vulnerable length classes. The thing that's important is not just this starting part of the selectivity curve, but also the end part. When fish are long, to what extent can you still catch them? And so this is the selectivity. This is when the gear is in the water, its potential to actually catch a fish as they grow larger, sometimes described as flat top or dome-shaped selectivity. And here we've got no reason to expect the fish to evade gear as they grow larger. So a typical reason why you might see this dome-shaped selectivity is because the fish move offshore as they grow older. They have an ontogenetic habitat shift to deeper water where there's lesser fishing, let's say. Or maybe they become faster and can avoid gear and more mobile and can evade gear more easily. Either way, you'd expect to see something like this. For the same unit of effort, you can catch a smaller fraction, relatively speaking, of these longer fish. And so in some fisheries, we expect there to be strong dome-shaped selectivity, but not in tiger flathead. One thing that's an important dynamic, obviously, that we haven't talked about in any of the previous questions is, well, what if they are discarding a large fraction of the fish? Obviously, this is really important for things like size limits. So for example, if you're going to, for all of your management procedures, discard rate matters to a certain extent, but discarding is important when you're going to say, you know what, beyond this size limit, below the size limit, you've got to throw it back. That's when discarding comes into place. So this is the background level of discarding here in question 12. And in this case, we're saying it's low. Naturally, they throw back between 1% and 10%. But in the next question, we ask what the mortality rate of that discarding is. And this mortality rate also would apply to fish discarded in a size limit management procedure or harvest strategy. So this is one of those things that would really affect size limits. And in this case, in the previous question, we've said that discard rate is low. Only about 1 in 100 or 1 in 10 fish are put back or thrown back in the water. But of those, almost all die. So in this case, with the base setup, let's say for a regular catch limit or TAC-based fishery, something like that, we've got between 1% and 10% going back and they all die. But if we had a size limit, a punitive or strongly a stringent size limit, this would become an increasingly important factor to distinguish between a input control as a size limit versus, say, a catch control or an effort control. So this is an important dynamic that distinguishes between different types of management procedure or harvest strategy. Of course, if this was low, let's say less than 5%, it wouldn't matter so much what we put in the discard rate. And similarly, if the discard rate was low, it might not matter that much that they all died. So in the base assumption, this one's like that. It doesn't really matter they all die, discard rates are low, but it will have an impact when we come to test a size limit. Recruitment variability is going to determine just how much stochasticity or background variability there is in the population. So this is going to control not only how much noise in the data that you're trying to sort of get signal from in terms of things like indices, but it's also going to affect how much productivity shifts you get. So how you might go through a few years of low recruitment and a few years of high. So this is going to distinguish more static management procedures from more dynamic ones. For the most part, we don't have particularly, it's not a particularly easy thing to characterize, but you could use, for example, an index of age one or small fish to try and get an idea for how much this moves around between years. You might be able to find some data to characterize it. For the most part, you're not going to have a great deal of certainty in this, but for the general pattern here, for example, in BC, is that lots of our long-lived species, like rockfish, tend to have more stable recruitment, and short-lived creatures tend to have quite high recruitment variability. That is not a general rule, however, and so this needs to be carefully thought out, and if necessary, default to unknown. So one type of management option that's available to us is spatial closures. Now, there may already be some in place in your fishery. You may have already have 10% marine reserves, a place where essentially fishing is not permitted. So this is a way you get to build that in, what's currently done. For tiger flathead, there's no spatial closure. Essentially, it's all open. Once you have specified a spatial closure, here it makes no difference really because there isn't one. But let's say you had chosen a 20% closure. Well, it also matters how much they move in and out of that area. So the effectiveness of a spatial closure that's existing will all depend on to what degree the fish mix between years. And this is where you get to choose that. So in a low scenario, 1%, very few fish are swapping between years. The lowest is none, and the highest when you select this box is a couple of fish. And you can see this highest scenario changing as we up the maximum rate all the way to fully mixed. And this means essentially fish move in and out of this area almost freely between years. And it doesn't take a great deal of mixing. Even up to 5% is quite a large degree of exchange between open and closed areas. So this will affect the efficacy of your current spatial closure, but we also have the same two questions for a future potential spatial closure. And that's what this one is. So here we say if we were to propose a spatial closure in the future, it could be between 10 and 20%. That's how big we want to make this potential or hypothetical future closure. And with that, we have to choose the mixing in and out of this hypothetical spatial closure. In this case, we're saying it's between 5 and 10%. So what you would do here is if you had tagging data or you had a similar species somewhere else, you would say this is the degree to expect fish to move between open and closed areas. And this is the bit where you specify that. And again, this is going to strongly determine a spatial closure harvest strategy against all these other types like size limits and effort controls and catch limits. But something we didn't deal with when we specified depletion was the idea that actually stocks can start out at quite low levels just due to either recruitment or maybe there has been industrial fishing of some sort prior to that initial year. This is where you get to choose that. If you think the stock is low and has been low for a long time, you might, for example, start it out at a low level. And this is a relatively difficult thing to specify. The usual assumption is that it's unfished before you went in, but you could certainly test the robustness of your harvest strategies to alternative scenarios, create multiple MERA models, or include some uncertainty in this. We have, believe it or not, got through all our fishery data, our fishery questionnaires, questions. So now we're on to management, characterizing the management and the data. So the second tab is all about what options are available to us for management and also how well management advice is followed. The first thing to realize about this initial question in management is that it doesn't affect any of the analyses that come up. It just affects color coding, so that you know which things you said were possible or not. So this is the bit where you say, well, I think total allowable catch control is possible. I can enforce a catch limit. I can specify and enforce it. TAE is a total allowable effort, so I can control the numbers of days of fishing or something similar. Size limit is a minimum size limit. Can I enforce such a thing? And what about spatial time area closures? In this particular example, for the benefits of this demo, all of those things are on the table. And like I say, if you were to untick, for example, TAC, in the results tables, they would be color coded to tell you that this is the performance of these management strategies, but guess what? You said they're not possible. It's just to keep track of that. And you can explain here a little bit more in this text box, all about why you think these things are available or not, or what it would take to get one of these working in practice. Let's say you do specify a total allowable catch. Well, on average, they might miss that. They might go over. And so this question tells you how much they go over, basically. And so if you were to choose between 150%, 200% of recommended, it's going to be up here, way higher. So the black line is what you actually asked for, and the blue is what they actually took. So in this case, we actually suspect slight overages. We think that they're going to overtake the TAC by between 0 and 10%. So we're building that uncertainty so that when we do set TAC advice for the harvest strategy, we've accounted for that. And that's important because that's going to be part of the feedback process. They're constantly going over We need an MP that can deal with that and deal with the feedback of fishing over the recommendation. We've got the offset. That was a small offset, but what about variability at that offset? So here we can see we've got lower variability. So on average, it's 5 to 10% higher, and it varies between 5 and 10%. So this is giving you this background level of noise in the implementation, inverted commas, error, the degree to which your advice was or wasn't closely followed. And you've got two distributions here showing you what the extreme values were. V 0.5 is showing you the low variability. V.1 is showing you the high variability. That's it in this range. And they're showing you for the 10% overage and the 0% overage that you specified in the previous question. So 0 is on the line, 10% is above the line. That's these two distributions here. And these are the different precisions that you've specified here. So this is just setting up your expectation for how well advice will be followed. In terms of TAE, you've got the same question, exactly the same question. And you've got the option, however you specify this, to just match what you said for the TACs. For the most part, you might say, well, I think they're going to follow the effort advice in the same way they might follow the catch advice. It's worth pointing out, however, that there are situations where you might expect a mismatch, and the effort control might be followed more closely than catch control. So we've got the same question about how variable that effort implementation would be, just like the TAC one. And last of all, we've got the same thing for a size limit. Are they going to catch below the size limit, and how much, and how variable will that be? And that gets us all the way to the end of the management questions. So we've just said what's on the cards and how well will it be followed, basically. So lastly, for our questionnaire, we have data. And the first thing you can do in data, which we're not going to do right now, is load a data file, a formatted data file of all the data you may have. And it doesn't have to be complete, but anything you've got will go into MERA and be used either for conditioning an operating model further or doing status evaluation. For the most part, you may not have very much, but this is where you'd enter it. For now, we're just going to move ahead, specifying an operating model, just using the questionnaire. So the first thing it's going to ask us is, in the data, is when we actually create and collect data, do we expect it to be reported accurately in these operating models? And in this case, we're saying we do. It's going to be plus or minus 5%, but you could say we don't know. And often you might expect this to actually match the overages and underages that you set in your management implementation, like the TAC. So if they go over, you might expect them to underreport by the same amount. I don't know. But this is where you get to choose, on average, how well your catch data come back to you. Another really important thing beyond catch bias is the hyperstability of the indices. This is controlling whether or not, if you get data back about relative changes in biomass in the stock, whether or not they move faster or slower than the true biomass. So for example, in something like, let's say, a purseine fishery, which targets aggregations, they might get a very high catch rate all the way down to some of the final aggregations, let's say. If so, that's called hyperstable. The index stays high, there's a high catch rate, even though the population is declining. In some fisheries, it's the opposite. So early on in the fishery, there are very vulnerable high density aggregations that are taken early. And after that, there's a massive drop in the catch rate that you see as you move to this other kind of subpopulation. And so that massive decline at the start in catch rate is not reflected in the biomass of the population. And those are called hyperdeplete. So you've got to think a little bit about your dynamics here. For example, in a reef fishery, you might go from one reef to another fishery, depleting in sequence the vulnerable biomass that's there. Just like the purseine fishery, well, that catch rate might stay high, even though the population biomass is actually dropping low. That's hyperstable. So this is your time to think about whether or not the index you're getting back, and I've talked about catch rate indices, but whether the index you're getting back is going to give you a good signal or going to be essentially proportional to what's really going on with the population in the water. And so this is the bit where you say that. And for this fishery, the chances are that it's hyperstable, if anything at all. And that's why these two questions have been, these two answers have been ticked. There's some guides here on how to go about, thinking about what this could be in your fishery. But let's just have a look. So a hyperstable fishery looks like this, where it's all up here. So the relative abundance index in this case, it's dropping in a way that's actually, it's dropping in a way that's slower. You can see it's staying high up here, the blue line, relative to the real stock depletion down here, which is going fast. So, this is an example maybe of that per se fishery. Here's hyperdepletion. The index here is plummeting much faster than the true depletion of the stock. Anyway, let's stick with the default that they came up with. Last of all, is a very general question which asks you what the overall data quality is. We've asked about catch bias and hyperstability. Those are the big ones. But this is a place where you can characterize in general terms whether catches and indices are precisely or imprecisely observed, and how many observations you've got. And these are aggregated into basically 4 selections: perfect data, good data, moderate data, and poor data. And here are some guidelines on just how bad those data are simulated. And of course, it's really useful to have perfect data because you can see in principle, if you want, how well your management procedures would work if you had a really almost unbelievably good fishery sampling program, for example. So this can be quite a useful tool just for exploration. For the purposes of this one, we know it's a data-rich stock. We know they put effort into collecting surveys and so on, and getting age samples and all kinds of things. So the data quality is good here. We have now come to the end of our 30-question quantitative questionnaire. From now on, you've done everything you need to explore all the features of MERA. You can, for example, choose management planning mode now, come down here, select some MPs for testing, and press calculate. For a guide to management planning mode, you can click right here. Hopefully I get this right. Alternatively, you could load data and evaluate stock status. So remember that first data question here. You could load data in here and we could do a stock status evaluation and this mode here, stock status. And I will give you a guide to doing that right here. I actually have no idea how to do that, but it's going to work. I've seen other people do it. For now, we've done everything we need. We've got a fishery operating model. Just one last thing you need to know is if you go to reports, you can now detail this questionnaire that you came up with and fully document it in an automatically built report, which is what I'm doing right now. And so let's click on that. And here it is. So this is all the questions we just filled out with the justifications. And you can see we've got a green bar saying that every single question that we filled out, we provided a justification. With MERA, if you're going to have anything other than the most uncertain full range of answers, you need a justification. So this is to keep you honest and make sure that you've got some reason for narrowing the range of uncertainty. And really what we've done so far is what you might do in a first day at a meeting somewhere, which is basically get a group of people together that understand the science, management, and other aspects of the fishery, and characterize everything we think we know about this fishery in a questionnaire, providing links to documentation. So this is one aspect of MERA that's designed to be a synthesis of fishery knowledge, data, but at the end of it, not just have this, which is a document telling you all about it, but actually have an operating or useful management, fishery management evaluation tool. An MSE is available to you now. So you come out of that first day, not only with a full discussion of the fishery, but with a framework for testing ideas. And we're going to talk about more of that in the other MERA tutorials. So that's all for me for this tutorial. Thanks for coming along. Remember, if this was confusing to you or you felt like you need an introduction, we did have another 10-minute intro to MERA to give you some context. And the link to that is right. We'll go this side now, here. Thanks very much, everybody. And keep the feedback coming. My email is tom@bluematterscience.com. So please keep providing me with feedback and ways of improving MERA. Thank you very much.